Can a pressure vessel produced through additive manufacturing withstand the high pressures deep under the ocean? And if it can, what would it take to break such a vessel? I'm Stephanie Hendrickson with Additive Manufacturing Media, and in this video, we'll look at the development and testing of a 3D printed pressure vessel for unmanned underwater vehicles, or UUVs. There are two parts to this story. First, how and why 3D printed pressure vessels might be used for underwater vehicles or other applications. And number two, what taking a 3D printed pressure vessel all the way to failure can teach us about the quality of 3D printed materials. The pressure vessel you'll see in this video was produced by Big Metal Additive, located in Denver, Colorado. So a few years back, Big Metal Additive got involved in a project with the US Navy to evaluate the feasibility of 3D printing pressure vessels for unmanned vehicles. Why is the Navy interested in this? Here's Slade Gardner, president of Big Metal Additive.
Well, it turns out that these are long lead items, and assembling them from piece parts is actually quite difficult. So if you wanted to use joining to produce this tank, you would have lots of interfaces to be concerned about when the part's loaded. But that long lead time tends to add to the cost of these kinds of pressure vessels. And we can be very competitive with cost against traditional manufacturing for things like 21-inch diameter pressure vessels, but we can really be overly competitive with the schedule. We can produce these parts faster and deliver them faster than conventional manufacturing. We produced this part under a Navy Phase 2 SBIR. In this case, it was a pressure vessel for an unmanned underwater vehicle. And the pressure vessel is designed to contain all of the electronics while the vessel goes deep undersea. This pressure vessel that we tested was manufactured using wire arc DED, using our hybrid version. So we would start with a base plate, and then we would deposit the material on top of that base plate. We would machine the surface of every single layer of metal that we put down. That gives us a clean, flat, smooth surface for every metal deposition layer. It also defines the layer height. The material that we used for these pressure vessels was aluminum. It was a 5554 alloy, which is a typical aluminum for pressure vessels. And that part was produced, I would say that part was probably produced in about a week.
So the SBIR was successful in demonstrating that wire DED could be used to make pressure vessels for unmanned underwater vehicles. But if this SBIR is over and done with, why are we still talking about this part? Well, it turns out that there's more that can be learned from this component as a specimen of 3D printed material. And a few things came together to justify some additional testing. Additive Manufacturing Media visited a company in Houston, Texas called Stress Engineering that thinks very deeply about how to test different components, including those made additively. Here's Matt Sanders, Program Director for Aerospace and Defense.
We specialize in solving really hard problems. We do this through advanced analysis and testing. For additive manufacturers, we support the design of additive parts to make sure that they're good parts and will work as intended. We also help additive manufacturers on material selection and testing, where we can recommend materials based on a certain application of additive part, or in special situations, we can conduct testing to simulate an environment that an additive part will see.
So once Matt knew we were coming, he wanted to set up a test of a 3D printed part to illustrate some of the tools and techniques that can be used to gather information about 3D printing components. And so he reached out to Slade. This pressure vessel had already been tested by BAA Systems in the course of the SBIR work. And the key loading condition here is external pressure, so forces pushing in. And that's what that initial testing focused on. So for this new round of tests, Big Metal Additive and Stress Engineering wanted to focus on putting the part into non-optimal loading conditions, things that it was not designed for, and see what it would take to get it to fail. They really thought of this as a test of the material, but at the full scale rather than the coupon level. And there was actually a whole series of tests conducted with this aim.
The first testing that we did was cyclic fatigue testing under internal pressure. And so we applied from near zero to 500 psi internal water pressure for over 200 cycles. And the reason for this was to try to see if the additive material would crack under a multi-fatigue application. And after 200 pressure cycles, we did not see any leakage from the part or any damage to the material.
So there were no problems found in the cyclic fatigue testing. The testing that we witnessed was the next stage, the internal pressure test.
After we conducted the cyclic pressure testing, we then went to an internal maximum pressure to failure test. And the idea is that if there were any cracks that maybe were formed from the fatigue cycling, that those would be present during the internal pressure test and would cause the part to fail maybe sooner than expected. We wanted to see how much internal pressure the part could take before leaking. During the pressure testing, we were measuring certain things on the part in order to get an understanding how the material was deforming under the internal pressure load.
To monitor how the part's performing during the test, we have two triaxial strain gauges, so we can measure the strain during the test, convert that over to stress. We also have a digital image correlation system. Essentially what we do is we have these two cameras, and they're filming the part, and on this side, we have a speckle pattern. So it's a white paint with a black mist of speckles. And so there's special software that will track the movement of all those speckles. So we can get the same color contour plot that an FEA will say and say, hey, this is what the simulation will do, but we get it of the actual part that's what's really going on. So it's not an assumption or a calculation, it's how the part is really moving. So that's what these cameras will be doing. I also have here acoustic emission sensors. What these do, we use them for pressure vessel tests where it's basically a really fancy microphone and it'll listen for cracks. So as we pressure up parts and it starts cracking, it'll hear it and we can capture when that cracking happens or if it's growing or if it's staying stable.
Digital image correlation turned out to be the tool that showed the failure in the part before anything else, partly because it didn't fail as expected.
We were monitoring all those during the test and ended up leaking at a flange that had an O-ring seal. So since this part was not originally designed to undergo internal pressure, but mainly external pressure, that flange is a weak point for this type of loading condition. But it was good in that we saw that the additive material was able to withstand the internal pressure even after the fatigue cycling and did not fail. It was another non-additive part of that was the leakage point.
The 3D printed pressure vessel was holding above 700 psi when the O-ring failed and the flange started to leak. Stress engineering wasn't done just yet, though. They developed another series of tests using compression to see if they could get this part to fail.
So for the final test, we decided to do a compression load test with internal pressure. Due to the way that this part was designed or its geometry, the flanges created a weak point in order to try to get the additive material to fail. And so we designed a test fixture that could apply a compression load into the sample to keep the flange surface from separating or failing during internal pressure. And what this allowed us to do is to be able to really increase the internal pressure on this part way beyond what the flange was originally intended or designed to hold. We were able to apply over 4,500 psi, way beyond its designed internal pressure or pressure rating, to try to get the additive material to fail. And it still did not fail. In fact, even with that, applying over 1 million pounds of compressive inload to counteract the pressure axial load, the additive material still did not break or leak or crack under the extreme hoop stress that was coming from the internal pressure. After completing that test, our final step was we let the internal pressure stay at 0, and we just applied external compression to the part to see how much compression, just from an axial load standpoint, this additive material would be able to withstand before collapsing. And we were able to apply over 740,000 pounds of force pushing down on this additive part before it dropped load and beginning to just get squished.
740,000 pounds of compressive force was needed to finally break this pressure vessel. But you might have noticed something interesting. When it compressed, it did not compress evenly all the way around.
that was due to a change in geometry or stiffness of the actual part itself. So if you had seen the ID of the part, there was a stop-start area that was thicker than the rest of the part. And so that thicker part was a little bit stronger than the rest. And so the opposite side of that is what squished down first. And then the thicker part failed as the whole load came down across the part.
So an important point here to reiterate, even though this testing was done on a full-scale additive part, they were really more interested in how the 3D printed aluminum would perform. So it was more of a material test than anything else. But as you saw with that uneven compression, choices made about the design of the part and even artifacts from the 3D printing process can still have an impact on how the material performs. So it's necessary to consider both the material and the design.
The evaluation of a material's performance can kind of be done and then used for multiple different parts. It's still important to test a component by component testing because there you may have different new effects that could affect the performance of the part besides just the material. The geometry and also the build strategy, like you could build a cylinder this way and then this way, or you could build it, different ways, and those may affect the performance of the part. Conducting a test on a component level brings you that added confidence that that part with that geometry and that build condition will perform as expected.
Taking it all in context, what does this set of tests show us about 3D printed pressure vessels and about wire DED in general? I asked Matt and Slade for their takeaways.
So the conclusions we can draw from all this testing is that the additive material really performed well. In fact, it outperformed a lot of the non-additive parts that were incorporated into it. And the design features from additive that allowed for very complex geometries, even under fatigue and other loading conditions that it's not really designed to see, the additive material performed very well.
Before we did the test, I made some guesses about what it would take to rip the thing apart or to crush it. I think I drastically underestimated the amount of load that it would take to damage the tank. Long ago, when I first started in additive manufacturing, people said, oh, you're putting it together a layer at a time. It's just going to tear apart at the layer interfaces. Well, guess what? It really doesn't. This is good metal. This is good casting equivalent, forging equivalent, foundry equivalent metal that we're making. And so all the test results that we're getting from this just give us more and more confidence that the metal is good and that we can make structural parts with it.
So if you're interested in more on wire DED or other uses for metal 3D printing, check out the links in the video description. You can also visit additivemanufacturing.media and the AM Media YouTube channel. Thanks for watching.